VLSI lab NAND gate. So let's see the schematic of the NAND gate. So initially we are using the electric software, that's why I'm running the java electric.jar electric 9.07.jar. So now we are building the schematic of the NAND gate. Okay, so for the NAND gate, we already have the library that we used to create the inverter. So if you want to watch the previous videos, please go through it for the installation of this software and even how to create the schematic and the layout of the inverter. So you just need to go to the file and create new library. If you are for the first time here, I'm just clicking the open library, and we have this already created library. Just it has only the inverter. Okay, this is what we designed in the last two sessions. Okay, one is the layout and another one is the schematic. Now we need to click on the VLSI experiment, that is the main file, and right click on it and go to the create new cell. Okay, and here this is the schematic and the NAND gate we are going to create, NAND. Just type NAND and click OK. So in this experiment we are going to see how the delay has the relationship with the NAND gates transition. Okay, so just on the grid, now we are going to create the NAND gate. So for that, go to the components and we need the Pmos and Nmos. So here go to the Pmos. So NAND, before that, to design the NAND gate we need to know its structure. So I'm just going to open the text editor. Okay, so in the NAND gate means y, the output is equal to a dot b, that is the AND output, and complement. Okay, complement of the a dot b whole bar. So in the Cmos, whenever we have the okay, so this complement will be always the output of the Cmos. So this a dot b, that we can design by using the, it is the multiplication, right? A dot b means ANDing operation. So if you make the pull down network series that acts like the AND operation, pull down network, that means NMOS network. Okay, NMOS network need to be series. If NMOS network is series, then pull up network, that is PMOS network, it has to be in parallel. Okay, so now let's design this. So for that one, PMOS network, that has to be in parallel. So this one, and this is for a one input and this is for the another input. Two PMOS we need. And okay, let's zoom this. Okay, two PMOS we need, and NMOS, I'm selecting the NMOS, and we need one NMOS and another NMOS, that has to be connected in the series. Okay, so just align this. Okay, so I guess no, it's completely zoomed. Okay, so yeah, now I think it's properly visible. So now we just need to align this eye of the grid. Okay, we need to on the grid. Is the grid is on or off? Unable to see the grid. Okay, that's fine. Now we created like this, and join this, just left click and right click here, and similarly we even need to join this and this. Okay, and this is connected in series, and this one we need to give here. So just take this at this point. Okay, so just take like this, and instead of this, let's create like this. Okay, so yes, and we need to connect this here. So this is the okay, so here we can just have this little bit upwards and connect it here, and this also we can have little bit above and connect these two. So now we are connected this in a series, and these two we need to connect in the parallel. So this I need to connect here, and from here to here. Okay, so now this structure, you can, if it is confusing, if this diagram, I can do one thing, I can get in the middle and we'll connect like this. Anything is fine. Okay, yes. Now we need to have the ground, so click on this ground and place this here and connect this ground here, and we need to have the VDD, that's the power source, that one we need to connect here. Okay, so then we need the two inputs, that is A and B. So before that we will just connect this one. Okay, so this one and this one, that is for the A input, so these two we will connect. Okay, these two we will connect, and even this and this one we will connect. Okay, so this is we will connect in some good way. So for that, okay, let's click here, just click here, and click here. Okay, so how we can connect here? So okay, instead of this we will take this from here. Okay, from here to, okay, so from here to here we will take, and yes, these two for the inputs, and here we have the, okay, so here we have this input, so this is the input A, and another one, that is the input B, and the output we need to take it from the this, that is the mid of these PMOS and NMOS interconnections. So this is the output. Okay, so this is the output, and this is one input and this is another input. Okay, so now we have the width and the length is 2 and width is 10 for all. We are designing with this data. So width is 10 and length is 2. Okay, so now we change the width of all these MOS, and we need to create export for this input and the output. Create export, so Control E, and this is the input A, so we can call this as okay, A. Let's give this as A, and here click input. Okay, so where is input, and click OK. So this is the A, and here this is the B, and click input and click OK. So this is the B, and this is the output. So create expert and out, or we can simply give as y, okay, or v out, anything is fine. V out we will give, and output, click ok, and okay. So now we need to set the spice model for this Pmos and Nmos. So just select the Pmos, go to tools and go to simulation spice and set spice model. Similarly do this for all these things, okay, all the Pmos and Nmos. Go to tools, spice, set spice model, just drag like this and go to select this, okay. So select this, go to, okay, I just need to select this and go to tools, simulation spice, set spice model, and even for this select like this, go to tools, simulation spice, set spice model, okay. Then we need to rename the spice model to Pmos. We are including the c5 models.txt, therefore this is Pmos and this is Nmos and this is Nmos, okay. So now we rename this one. Now you can check once the DRC also. So there is a 3 errors, so let's see that errors. It may be something like wire or unnecessary connections. So if it is like this, just click on this and click delete, so it will delete that unnecessary wires or unnecessary connections. So here also just click delete. Now again go to tools, DRC, check hierarchy, there is no any errors. Here you can see 0 errors, 0 warnings, okay. So now we need to have the spice code to in order to work with this. Go to the components and MISC, and here we can find the spice code and have it somewhere here, and just click on this Control I and go to the select multi-line text, and now we need to write the spice code. So for this first thing is this VDD and ground, it will take automatically. We need to write the voltage for VDD. So VDD 0 DC 5, and we have the two inputs, that is A and B. So we need to give the pulse for A and B, okay, pulse. That means A and B has to be 0 0 0 1 like that. A and B we need to give the pulse. So for that one the voltage name that has to start from V, okay, VA, voltage name, there is just a name, and that is between A and ground, okay. I hope you understand, that is between A, one terminal is connected to A and the terminal is connected to ground. It's just like the battery cell or like that power source. VA0, and we are using the pulse command, pulse. So initially pulse value is 0, then the final pulse value is 5 volt, and the time delay, that is TD is 0, and rise delay we just give as a 1 nanosecond, and fall delay we just give as a 1 nanosecond, okay. So 2 voltages and 3 delays, and the pulse width, okay. So pulse width we will give as 5 nanosecond, and the time period we give as a 10 nanosecond, okay. So 5 nanosecond and 10 nanosecond, that is the time period. Then for VB, that also similar command, pulse command only we need to use, but we will change these pulse order. That means this pulse width we will make this as a so we will make this as the pulse width as okay, so 810, and here we make this as instead of 8n we will just try. Okay, we will make this as a 10n, and this as the time period as 15n. Okay, so we need to get the all the combinations like 0 0 0 1 1 0 1 1. So later we can change this. And this is okay, so this is VB, and here we are providing it the VB, and we need to do the transient analysis. So dot tran and for 300 nanosecond we will do. Okay, so and we need to include the dot include and CLUD dot include, so which is that file C5 models.txt. okay, so C5 underscore models.txt. so this we need to write. Yeah, here no any quotes, just simply dot include C5 models.txt. okay, so now click apply and click OK. And this technology is, I guess, the Cmos that only selected. So technology and scale, so Cmos. okay, and yeah, now let's run this. Go to tools and click simulate spice, write spice deck. So yes, we have here. Later we can change this. If we not get all the values, we can change these pulse commands. And here let's display the waveform. Okay, add traces, and here VA and VB and V out. Okay, so just click OK, and just add the plot plane. Just to differentiate these waveforms, add plot plane, again add the plot plane, and VA and VB and V out. So we need to get all the combinations here. So for that one we will just check. Okay, so I'll just zoom this, and we will just check for this part. Okay, so here first, okay, so this is the A is okay, so this is A1, and A is becoming from 1 to 0, that is A is becoming low. Initially A is at 1 and B is also at 1, and A is becoming low. Okay, so now that means it is the 0 1 combination. Initially it is 1 1, then the A is transiting from 1 to 0. Okay, so if A is transiting from 1 to 0 means actually the thing is, when both the inputs A and B, both the inputs, if they transit from 1 1 to 0 0, then the delay will be less. And if only any one of the input like A or B, which is transiting from 1 to 0, then the delay will be slightly more. In that, if A transit first, that means here in this diagram, okay, so in this diagram A is connected to the inner transistor, and B is connected to the outer NMOS. Okay, so if A transits from 1 to 0, it only needs to the output capacitances are there, right? This only the it is connected to this output capacitances A. so it only need to charge the output node capacitances. But whenever the B transits from 1 to 0, it has to uh, like charge both output capacitance as well as the internal node capacitances. So the transition slows down. So that's why we have to see the three things. One is okay, so A and B. Okay, so then here okay, so A and B. So here, okay, this is our observation, A and B, when so here these two for the, okay, so initially then A and B, this is the finally. That means initially it is like this, then it will changing to the this value. So those things we need to observe. Okay, so for that one we will understand this table exactly. So AB initially 1 and 1, then A is transiting from 1 to 0 and B remains in 1. This is one thing we need to observe. And another thing is initially A and B is 1 1 and A is remains as 1, B is transiting from 1 to 0. And another thing is 1 1 and this is transiting from 0 to 0. Both will transit. Okay, both will transit from 1 to 0 and 1 to 0 transition. So now for this one we need to measure the TD, and if you want we can measure TP, LH and TPHL also. So TD will measure the TD, that's the delay time. So here for for this case we have just got in this waveform. So here, okay, so I will just going to zoom this, and here we can see the A is transiting from, A is initially 1, B is also 1, and A is transiting from 1 to 0, B is 1. So at this point what is the output, or what we can see, okay, at this point. So for to measure this, the delay, so initially A and B is 1 1. That means in the NAND gate 1 1 means the output has to be 0. Okay, so we will be have the one cursor here, so it is at 0. Okay, so it is at 0. Okay, it is at 0. Then this A will transit from 1 to 0. Okay, B is in the 1 only, A is transiting from 1 to 0 at this point. So we need to measure the TD. So for that one okay, so at this point, okay, so it is transiting, so let's zoom this. Okay guys, 1 minute. Okay guys, actually the measuring of this TD and TPLH here little bit confusing, so let's see how we can do, like how to measure this properly. So how to measure TD, delay in Cmos. So now we can see here there are some definitions are there, 4 definitions. Okay, so let's this file to load. Okay, so let's follow this now. Here we can see, Okay, so yeah, we can see these definitions. So one is the TR and TF. So these two we not measured. We measured TPLH and TP low to high. Those two we measured. And another is the delay time, TD. Okay. So this is the another method. One method is we did in the inverter by taking one cursor to the zero and the cursor to the starting. So this is the another method. So delay time, TD, time difference between input transition 50% and the 50% of the output level. That means we need to go to the waveform and just zoom this part. Okay, so let's have the cursor. One cursor is at the input. Okay, so this is for the input, and another cursor is at the output. And we need to, okay, so we will just take this cursor nearer to the our first value and just have the zoom over these things. And the cursor 1 we need to keep at the 50% of the input transition, that is 2.5 volt. Okay, and we still even zoom these things. And another cursor we need to keep at the 50% of the output transition. So the 50% of this one, this is the output, so 50% we need to keep. So this comes nearly at this point. Okay, so it is not exact value but somewhat it comes here. And we need to measure this delay, that is the difference. So this is the TD value we get for this transition. Okay, so this is the TD value we got for this transition. And similarly we need to measure the TP high to low and TP low to high. So for that one, um, okay, so here we can see T1 minus T0. Okay, so T1 minus T0, that means they are considering the 50% of the transition. Okay, so 50% of the transition from this one to this one they are considering. So okay, so let's see some in some images, or what is TPLH and TPHL. So okay, here we just go here. Okay, so some Edu website we got. So let's see here. Okay, so here we can see that TPHL, that is okay, so they measured TPD. Yes, TPD means TD we measured. Okay, so here it is not there. Okay, we follow our usual easy method. So I just thought of findings in some other method. We just use that same method. So for this one, the TP low to high, that is from, okay, so cursor to, okay, so these two cursors, no, we need to consider this part and go to this cursor. Okay, so okay, so here we need to select the cursor, and one is for TP. Okay, so at this point, and another one is the low to high. Okay, so this is what we got. But if you measure the low to high like this, it depends upon the this one. Okay, the time delay for this input to change. So here this is 994 point. Okay, so this is what we got. So that is only one delay. Let's measure. So that is low to high. Okay, so low to high we got as TPLH. We got as this one. And similarly, if you want, you can measure high to low. So that you can consider in some other transition we need to consider. Here it is not possible, so because it's changing from low to high. So now when B transit from 1 to 0, so that we need to search wherever the B transits from 1 to 0, and yeah, here we can see A remains in 1 and B is transmitting from 1 to 0. So is there anywhere we can get the better waveform? Let's just zoom and let's see. So A has to be 1, and B has to transit from 1 to 0. So if not, we just change this time period. So this is pulse width. Pulse width we keep as same, and this one we just make as 20n, and let's run this. So now let's check. So okay, so a we will make this as a 20, and this 20, and this we make as 5. So we may get, okay, so A has to remain in 1, right? Means this one we need to make this as 15. Okay, so A has to remain in 1. Okay, so and B has to change from 1 to 0. Okay, so here we can see. Okay, so here we can see A remains in 1, B is changing from 1 to 0. Okay, A is remaining in 1, B is changing from 1 to 0. So at this point, okay, so 1 is the input. Okay, so where is that cursor? VA. Let's zoom this. Okay, I guess it's here. Just take the zoom of this part. A is 1 and B is going to 0. So okay, at this part we can see A is 1 and B is going to 0. So just keep it in the, okay, so we selected VA, but we need VP. Okay, so okay, so two things we need, VB and Vout. So let's zoom here itself and let's see. Okay, here we have B is transiting to 0, so this one we need to keep it as 50%. Okay, and this one we need to keep at the 50% of the output, that is somewhere here. Okay, so now we get this delay as, this is what the delay we got, that is the TD. Okay, so this is what we got. And so here we have seen if the A is transiting from 0 to 1, that means 1 to, if A is transiting from 1 to 0, it only need to charge up the output node capacitance, so the delay will be less. But here it has to charge both the output node capacitance as well as the internal capacitance, so the delay will be more. Now okay, so you need to measure this also. So now let's measure the TD for this one, that is 1 1 to 0 0. For this transition, both has to go from 1 1 to 0 0. So let's go to the spice and we'll keep both as same, and we'll run this. So both are 1 1, then they are going to 0. So now we will measure the TD. Okay, just I will zoom this. Okay, so two cursors, is the cursor 2, okay, and this is the cursor 1. So we will zoom this part. And so push cursor, keep it as the VA and VB, right? So from 0 to, okay, 0 to 5 volt it is. So okay, so 0 to 5 means 2.5 we need to keep, yes. And this is for the output. So this one we need to keep at the, okay, we will just zoom this. So this 2 we need to keep at the, okay, so the 50% of the, okay, so here 1 we need to keep at 50% means 2.4. Okay, so yes, it is now at the middle. And this value, this mod value we need to consider. So here, okay, actually this has to exactly in the center, and this one needs to be at 2.5. so 2.5, here it is going 5.4 scale. So okay, so we will just keep, so 2.4, 6 means 2.5. okay, so this is maybe the proper, okay, we got something like this. So here the delay has to be less, okay, somewhere nearer to this only we got, but here we got in negative, right? That means it may be like the sudden transitions or like that. Okay, so actually we need to get like that. So here 2 just to be exactly the middle. And this also, okay, so this is 1, right? Yeah, this we will take it here for the A. We'll take this here 2.5, and this B, another cursor, this another cursor, so somewhat this value we are getting. Okay, so 48.41 picoseconds. So this value has to be slightly less than this. So it's roughly like these values we got. I hope you understand this theory behind this. So this is the schematic. In the next video we will going to see how to construct the layout for this NAND gate. So we can have the observation here. So from whenever it is transiting from 1 to, when both the nodes 1 1 to 0 0, at that time the delay will be less. And if any one of the node which is transiting from 1 to 0, if the inner node, that is A, which is transmitting from 1 to 0, then the delay will be less, because only the output capacitances need to be charged, output node capacitances. But here, if the outer node which is transiting from 1 to 0, then both the output capacitances, the output node capacitance as well as the internal node capacitance need to be charged, so the delay will be slightly more when compared to this one. Okay, I hope you understood this. Thank you.